Hello there, this is Mr. Sutton, and you're joining us for the first in a series of lessons on radicals. In this one, we'll figure out how to simplify square roots of constants, and we'll figure out how long a ladder needs to be in order to reach the top of a building. For your warm-up, here are four numbers. See if you can figure out which perfect squares they are divisible by. All right, let's see if you got them all. 20, that's divisible by 4. 48 is also divisible by 4, but also 16. 98, that's divisible by 49. And 1300, that's divisible by a few things. So 4 is definitely going to go into this because 100 does. 25 is going to go into this because 100 does. And, oh yeah, 100. Before we go through the difficult task of simplifying radicals, let's go over a few important definitions and rules. First off, when I say the word radical, we're talking about the square root symbol. And if we're being technical, there are other types of roots as well. There's cube roots, fourth roots, fifth roots, and they're all radicals. But for now, this chapter, we're just going to deal with square roots. The number inside the square root, we're going to call that the radicand. And when we say simplest radical form, we are saying that the radicand, the number inside the square root, does not have any perfect square factors. There are other things that we need to do for simplest radical form that we'll see later on, but for this lesson, all we care about is perfect square factors inside the radical. Now, there's two rules that are going to help us with this. One rule, which I like to call the move-in rule, says that if you have two radicals being multiplied by each other, you can multiply them under one big radical. And just as there's a moving-in rule, we can actually go the opposite direction with the move-out rule. And this says that if you're able to split up the stuff inside a radical into two factors, you can give each factor its own square root and multiply the two square roots. So we're going to use these two rules to do all the radical simplifying in this chapter. Let's go ahead now and see how we can use the moving out rule to simplify radicals. So the way we're going to use this, we said that if we can split this up into factors, we can give each of them their own square root. So we are going to split this radical into the biggest perfect square factor times a non-perfect square. These are both going to be in square roots. So pause the video and see if you can figure out the biggest perfect square that goes into 48 and the factor that you'd have to multiply that by. Do you have it? So 16 times 3, that's the best one here. There are other perfect squares that go into 48, but 16 is the biggest out of the bunch. Once you've got this split up into a perfect square times another number, you're going to square root the perfect square, and the square root of 16 is, that's right, 4, and leave the non-perfect square inside the square root. So a simplest radical form basically means that everything you could factor out and square root has been square rooted. We're going to do this problem over again now. Now let's say that you hadn't figured out 16 was the best perfect square, and you went with 4 times 12 instead. Well, you can still fix this if you're actually looking out for perfect squares after the fact. So if you don't use the biggest perfect square in the beginning, you can keep going. In fact, you have to simplify it. So 2 radical 12 is what we would initially end up with, but then you look and say, oops, 12 is actually also divisible by 4. So you can keep going and split the 12 up into 4 times 3. The square root of 4 is 2. And this 2 now gets multiplied by the 2 that was already outside to give us with the same answer as we got up here, 4 radical 3. So again, not the end of the world if you don't use the biggest perfect square in the beginning. In fact, you should always be looking at your answer to make sure you didn't forget any perfect square factors. We're going to do this problem one more time, though. Some of you are probably sick of seeing this by now. But I'm going to give you one more way of doing this called the buddy system. And this is a great method if you just have no clue about perfect squares and you just want to split this up any which way. So the way we do this is we're going to break our radicand into factors again, but this time we're just going to go for the easiest factors that we can think of, and we're going to keep going until we can't split anything up anymore. So 48, let's divide that by 2, right? Because it doesn't get any easier. So we've got 2 times 24, but now 24 we can split up into 2 times 12, And 12 we can split up into 2 times 6, and 6 is 2 times 3, of course. So now once you've got these factor trees and you have these leaves here, these dead ends that you can't factor anymore, what we're going to do with those is we're going to look for matches. Whenever we can match 2 of those leaves, 2 of those factors, we're going to get one non-radical version of that number down here in our simplified form. And what this rests on is the fact that these here are really all inside radicals. If you're splitting up radical 48, you've really got radical 2, radical 2, radical 2, radical 2, and radical 3. If you multiply a radical by itself, if you square a square root, then you end up getting the number that's inside. If you have radical 2 times radical 2, that's radical 4, which we know the square root of 4 is just 2. So let's match things up now. 2 times 2, or radical 2 times radical 2, that's just 2. We have another match of 2's here. That gives us another real 2 over here. And then any numbers that don't have buddies, those are just going to stay inside the radical and get multiplied together. So the only odd one out is this 3. So that's just going to be a radical 3. And then just multiply through. So again, we get the answer 4 radical 3. Now the buddy system is nice if you don't know too much about perfect squares. You can see where it could get a little bit nasty, though, if you have some larger numbers inside here. So it is good to try and find the biggest perfect square if you can. Now that you've seen some methods for simplifying radicals, simplify these 2 radicals, pause the video and try it, using whichever method you want. All right, let's see how you did. Now, I'm never going to use the buddy system because it's very rarely the most efficient method. But again, if you can get my answer using the buddy system, more power to you. So this first one, I'm trying to think of perfect squares that go into 98. And 49, I know, goes into 98. 49 times 2, square root of 49 gives us 7, so 7 radical 2 for that one. Over here, I know 20 can be split up into 4 times 5. The square root of 4 is 2, and 2 times negative 5 is going to give us negative 10. We're going to do one more problem. This one's going to have a real-life application because you might be wondering, how can simplifying radicals possibly be useful in real life? So let's say we have Sierpinski. Here he is. He's come to save a princess from certain death at the hands of some evil king. The only thing stopping him is a castle wall that's 30 feet high and a monster-inhabited moat that is 20 feet wide. There's a monster. Woohoo! I'm a monster! All right, so we want to know how long the ladder needs to be in order to reach the top of the castle wall. So here's our ladder. We got it at Lowe's or Home Depot. It's one of the extendable kind. No, actually it isn't. This is medieval times. It's actually a wood ladder, but this is the only picture I could find. So how do we do this? Well, we know that we have a triangle formed by the ladder in the wall. Let's pretend this castle wall is perfectly straight so we get a nice right triangle. And we know that we have 30 feet going up, and this is not drawn to scale, but we have a 20-foot moat, and we are looking for this third side, aka the hypotenuse. How do we find the hypotenuse in the right triangle? You got it. A squared plus b squared equals c squared, the Pythagorean theorem. So we've got 20 squared plus 30 squared equals x squared. This is 400 plus 900 is 1300. And then the square root of both sides gives us the square root of 1300. Unfortunately, oh no, Sierpinski forgot his triangle. Gosh, Sierpinski. So what we're going to have to do is figure out how to estimate this square root without a triangle. And this is actually a skill that they're asking for more and more on standardized tests. At least the Massachusetts MCAS wants you to be able to do this. So let's see how we can make our lives a little bit easier. Go ahead, pause the video, and see if you can simplify this radical, and then we'll take it from there. You think you got it? So this is not a very good one for the buddy system. There's a lot of things you'll have to split this up into. But for perfect squares, we know that 100 has got to go into anything with 2 zeros, right? 100 times 13. So that's going to be 10 radical 13. And we can now estimate this. Now the square root of 13, what is that? Well, that's between the square root of 9, which is 3, and the square root of 16, which is 4. So we've basically got 10 times 3 and 10 times 4. That's the range of what our ladder should be, so between 30 and 40 feet. Now, realistically, if you're Sierpinski and you're building this ladder from scratch, you probably just want to make it 40 feet to be on the safe side, but at least you know what to expect. And that concludes this fairy tale. Until next time, this is Mr. Sutton signing off, and they lived happily ever after.